Hello everyone, we are Lucia and Andreas.
In this video, we're going to try to make a summary of our praise summer of HPC project titled Quantum Algorithms and Their Applications. First, we want to highlight the importance of quantum computers by making a comparison with classical computers. The main differences between them are described here, although the most striking one is the use of qubit in quantum computers, a quantum system that can express states 0 and 1 at the same time, so we can process more information with qubits than with normal bits, enabling quantum computer to do certain calculations much faster than the conventional computers. Quantum computing uses different properties of quantum states. We are talking here about superposition and entanglement. In order to achieve them, we introduce the concept of quantum gates, which are nothing more than unitary matrices that perform operations on qubits. We can highlight the Pauli gate, Hadamard gate, and CNOT gate represented in our slide. Being unitary matrices, we can see that if we represent the qubit on the Bloch sphere, applying X gate, there is nothing more than performing a rotation around the X-axis. Another important element of quantum computing are the circuits, a set of qubits and gates where we implement the algorithms. Here are the main features that compose it. So let's start talking about the actual project. This is an index of points we have dealt with in the project. As we do not have time to talk about all of them, we will concentrate on the source algorithm and the results obtained from it. We use source algorithm for number factorization. It is a hybrid algorithm that it combines quantum computers and classical computers to get the most out of both. With the quantum implementation, we are able to solve the problem of factoring a number in polynomial time, thus breaking encryption systems such as RSA, whose security lies in the problem of factoring integers. We begin by describing the algorithm. Starting from the integer n that we want to factor, we choose an integer a smaller than n. We calculate the greatest common divisor of a and n. If it is different from 1, it means that a is not a trivial factor of n, and we finish the algorithm. Otherwise, we use the quantum algorithm, which will give the period of function f of x. If r is odd, we go to step 1. If a at the power of r over 2 is concurrent with minus 1 mod n, we return to the first step. We obtain the two factors by calculating the greatest common divisor of a at the power of r over 2 plus minus 1 and n.
So, for our first implementation, we tried to factorize number 35 on a real quantum computer. In this slide, we see the description of the algorithm using a equals 6. The first step is to apply Hadamard gate to the first two qubits in order to have them in superposition state, and a next gate to the third one in order to use it in the two custom functions that we built. Then we used the two custom functions, the oracle that we built for 6 modulo 35 and 6 to the power of 2 modulo 35, taking as an input the first and the second qubit, which are in superposition state for each case. The last step of the algorithm is to run an inverse quantum Fourier transform on the two first qubits and then measure them. So now we're going to try to explain how the oracle actually works. It's quite simple. We basically change qubit 0 and 2, and then we apply the next gate to qubit 1. What we want to achieve is that if the input is number 1, then the output is number 6. And if the input is number 6, then the output is number 1. It's a bit tricky, but we end up getting a series 1, 6, 1, 6, etc. So once we apply the quantum algorithm, we get the results, which are displayed in the histograms, giving higher probability to those results that the algorithm considers correct. The value whose probability stands out apart from 0, which is always a possible value due to the inverse quantum Fourier transform is 1, 0, 2 in decimal. We can take this as the R period because the search period R is calculated as the ratio of the total number of possible outcomes, which in this case is 4, and the smallest non-zero outcome, which in this case is 2. Also, the period R can be determined as the number of peaks of the probability histogram, which, as can be seen, is again the number 2. Outputs 0, 1 and 1, 1 with smaller probabilities are due to the inaccuracy of the quantum computer used, so we neglect them. If we use the simulator instead, the probability would be 0. We finish the algorithm by following steps 5, 6 and 7 and obtaining the numbers 5 and 7, which effectively, when multiplied, give 35. So let's complicate things a bit and take a larger number, for example number 91. In this circuit we have used 13 qubits. Except for the number of times we apply the oracle, the circuit works exactly the same as the previous one. We have to run this circuit in a simulator because the free version of IBM quantum computer did not allow us to use more than 5 qubits. With this oracle, we try to get something similar to the previous example, only using 4 modulo 91. So when we have 1, we want to get 4. When we have 4, we want to get 16, and so on. So here we have an histogram similar to the previous one. In this case, to obtain the result R, although there are other methods, as we described, we are going to look at the number of peaks in the histogram. We see that there are 6, so we can deduce that R equals 6. So for finishing, in the same way, we finish the algorithm seeing that R is even, that step 6 is not verified, and that the factors are numbers 13 and 7, which effectively, if we multiply them, obtain 91. So finally, we would like to mention that in this summer of internship, we have experienced the creation of quantum algorithms by running them on simulators and quantum computers. We have realized the power of quantum computing and how they will play a key role in high-performance computing if we get over some current problems like the inaccuracy and being able to bring a large number of qubits into controllable quantum states. We're talking for about 1 million qubits, although details depend on the quality of qubits and the problems you are trying to solve. So the major question for quantum computing isn't if it's going to work. We know it works. The real question would be, will it scale?